Imagine an element on the periodic table that carries the name of an entire continent. Americium, element 95. You could call it the most patriotic element, but it's actually literally named after the Americas. But its story goes far beyond symbolism. This silvery radioactive metal was born in the secret laboratories of World War II, and today it quietly works behind the scenes of millions of homes. In this video, we'll journey through the history of Americium, how it was discovered during the Manhattan Project, why it earned its name, and what makes its properties so unique. How do we produce it? And the surprising ways it is used, including in the humble smoke detector right above your head. Welcome to Q Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, subscribe, hype, and hit the notification bell so you will never have to miss another episode. Also, make sure to fill in the poll in the post section of the channel for next week, as we, of course, will not be discussing calcium again. Americium is a silvery white metal when freshly prepared, with a shine similar to aluminum or polished silver, though it quickly dulls as it forms a thin oxide layer like most metals. While it looks like an ordinary piece of metal, but we don't have it in this cube. Unfortunately, we do not have it in this cube, and the reason is probably because it is not sold in these quantities and it would be too radioactive and probably too expensive. Now, if we would have it here, and it looks so ordinary, could you lick it? Well, licking it would be a very different matter depending on whether it's sealed or unsealed. A sealed americium source, like the tiny well-encased pellet inside a household smoke detector, poses virtually no danger if touched or even licked on the outside of the casing, because its alpha radiation cannot penetrate metal or skin. However, licking unsealed americium metal or any loose americium compound would be dangerous, as it also states in the periodic licking table. Even a microscopic amount taken into the mouth could be swallowed or absorbed, allowing radioactive particles to enter the body. Inside the body, americium tends to accumulate in bones, the liver, and the kidneys, where its alpha radiation can damage tissues and increase long-term cancer risk. Although licking unsealed americium would not cause instant burns or immediate radiation sickness, it would be considered a serious internal contamination incident requiring medical treatment. Plus, what is wrong with you? Why would you want to lick it anyway? The story of americium begins in the midst of World War II under the veil of the Manhattan Project, the top-secret effort to build the first atomic bombs. In the late 1940s, a team of scientists led by Glenn T. Seaborg at the University of California, Berkeley, working with the Met Lab in Chicago, succeeded in creating a brand new element. They bombarded plutonium with neutrons in a nuclear reactor and then used a cyclotron, a type of particle accelerator, to further irradiate the material. After a series of complex chemical separations, the researchers isolated a few micrograms of a substance that has never existed on the Earth before. They had produced element 95, later named americium. Now, it wasn't easy to get those first specks of americium. The element didn't reveal itself readily. Seaborg's group spent over a year painstakingly separating americium from element 96, curium, which they created at nearly the same time. The two elements' chemistry was so similar that the frustrated scientists jokingly dubbed them pandemonium and delirium, because the separation process felt like an hellish madness. Finally, by autumn 1944, they confirmed the new element's identity by its radioactivity. Americium was actually the fourth transuranic element ever discovered, after neptunium, plutonium, and curium, even though its atomic number is 95, one lighter than curium. This out-of-order discovery happened because curium was identified slightly earlier, a quirk of the experiment's timing. Secrecy shrouded americium at first. All research on transuranium elements was classified during the war. It wasn't until VJ Day, Victory over Japan Day, in 1945 that the public learned of element 95 and 96. In an interesting twist, Glenn Seaborg leaked the news in a most unexpected way on a children's radio quiz show. On November 11, 1945, Seaborg was a guest on the popular radio program Quiz Kids, when a child on the show asked if any new elements besides plutonium and neptunium had been discovered during the war. Seaborg couldn't resist. He revealed that 2 more elements, 95 and 96, indeed had been found. Teachers around the country were startled to hear a scientist telling kids to update their textbook from 94 to 96 elements. Just a few days later, Seaborg formally announced americium and curium at the American Chemical Society meeting. The secret was out. The periodic table had now gained 2 new members. Now, in those days, only tiny amounts of americium existed, far too little to see it with the naked eye. The first samples were just micrograms, millions of a gram, detected only by their radiation. It wasn't until 1951 that chemists were able to produce a measurable chunk of americium metal, still only a few tens of milligrams at most. Now, they did this by reducing americium fluoride with barium metal in a high-temperature vacuum furnace, finally yielding a pinhead-sized piece of metallic americium. This milestone allowed scientists to observe americium's appearance and basic properties for the first time. Now, why do they call element 95 americium? Well, Glenn Seaborg and his team chose the name to follow a geographic naming pattern. In the periodic table, americium falls right below the element europium, which was named after Europa. By analogy, the new element was named after the New World, the Americas, where it was discovered. The choice was a nod to the continent of North America and by extension South America too, effectively making americium the element of America. Seaborg proposed the name and the chemical symbol AM, and it became official. Now, the name Americium certainly sounds patriotic, evoking the United States or the American continent. However, the intention wasn't chest-thumping nationalism so much as keeping with tradition and acknowledging the place of discovery. In fact, many elements are named after locations or countries. For example, polonium for Poland, francium for France, and californium element 98 for the state of California. In Americium's case, it immortalized an entire pair of continents in the periodic table. Interestingly, the Americas themselves got their name from Italian explorer Amerigo Vespucci. So, indirectly, americium shares a linguistic lineage with a 15th century mapmaker, making it one of the few elements, along with others like samarium and gadolinium, that are indirectly named after people, in this case via a place name. During the research phase, as mentioned, the scientists humorously referred to americium as pandemonium before the official name was decided, a joke reflecting the chaos they endured in isolating it. Like mentioned, americium is a silvery white metal when it's freshly prepared. If you could hold a piece of pure americium, which you shouldn't without precautions, it would look shiny and metallic, somewhat like freshly cut aluminum or silver. However, that bright luster doesn't last long. The metal tarnishes slowly in air. Americium readily reacts with oxygen to form a thin layer of americium oxide on its surface, dulling the shine. This behavior is similar to many other reactive metals, although americium tarnishes more slowly than some of its periodic table neighbors. In terms of weight and feel, americium is quite heavy, but surprisingly not as dense as some other actinides. Its density is about 12 grams per cubic centimeter, which means it's 12 times heavier than water. It's denser than common metals like iron or copper, but it's actually less dense than plutonium. Plutonium is significantly denser at about 19.8 grams per cubic centimeter. Americium metal is also relatively soft and malleable. You could flatten it with a hammer or cut it with some effort. It's not a hard, brittle metal, it's more easily deformed compared to earlier actinides like uranium. In fact, americium's crystal structure and bonding make it have a lower bulk modulus, meaning it's not as rigid. All these qualities indicate that americium is a rather normal-looking metal to the eye, albeit a radioactive one that you can't casually handle. Americium has a high melting point of around 1176 degrees Celsius or 2149 degrees Fahrenheit, which is higher than the melting point of pure plutonium and higher than that of its lanthanide analog europium. So in terms of heat resistance, americium stays solid until very high temperatures. If you heat it further, about 2600 degrees Celsius, it will boil and turn into vapor. Though doing this would release radioactive fumes, definitely not something to try in your kitchen. Being an actinide element, americium is radioactive. All of its isotopes are unstable, meaning they will decay over time by emitting radiation. The most important isotope of americium is americium-241, written as this, and this is the isotope we typically use and encounter in devices. Americium-241 has a half-life of about 432 years. Half-life is a term that means the time it takes for half of a given amount of radioactive substance to decay. So over 432 years, half of any given quantity of americium-241 will have transformed, decayed, into other elements, primarily neptunium-237 in this case. Because of these long half-lives, americium doesn't vanish quickly, which is both a benefit for long-term uses and a challenge for radioactive waste management. What kind of radiation does americium emit? Well, mostly alpha particles. An alpha particle is essentially a heavy positively charged chunk, the nucleus of a helium atom, 2 protons and 2 neutrons bound together. Americium-241 primarily undergoes alpha decay, spitting out alpha particles. Now, these alpha particles don't travel far. They can be stopped by a sheet of paper or even a few centimeters of air. This means that outside the body, americium's alpha radiation isn't very penetrating. However, alpha emitters can be dangerous if they get inside your body. For example, if americium dust were inhaled or ingested, because then the alpha particles can damage living tissue internally. Some americium isotopes or their decay products also emit a bit of gamma radiation and even neutrons, which are more penetrating. For instance, americium-241's decay eventually produces some gamma rays of about 60 kiloelectron volts of energy. Not extremely powerful as gamma rays go, but enough to be useful in certain applications, and we will get to that later. When americium-241 is mixed with certain materials like beryllium, it can produce free neutrons. We will cover that in the uses section. One intriguing aspect of americium metal is that its own radioactivity gradually damages its crystal structure. The constant barrage of alpha particles shooting out from americium atoms knocks atoms out of place within the metal over time. In a sample of americium metal kept at low temperature, you can actually observe the metal's properties changing as radiation damage accumulates. For example, electrical resistivity creeping up. At room temperature, some of that damage self-heals. Chemically, americium behaves a lot like its neighbors in the actinide series, and somewhat like the lanthanide elements above it. In compounds, americium most commonly shows a +3 oxidation state, americium 3+, which means it typically loses 3 electrons and forms trivalent ions, similar to how europium 3+, or other rare earths do. In fact, the +3 state is the most stable form of americium in a solution, which was a big hint that led Seaborg to realize that actinides like americium belong in a series analogous to the lanthanides. Americium 3 compounds tend to have that pastel colors, for example. Americium 3+ in solution often gives a yellowish or pink hue depending on conditions. What's remarkable is that americium can also exist in a variety of other oxidation states, +2 all the way up to +7 under the right chemical conditions. This is a wider range than most actinides can achieve. For example, you can have americium dioxide where americium is in the +4 state, or you can dissolve americium in very strong oxidizing solutions to get americium 5 or americium 6 species that form ions analogous to uranium's famous uranyl ion. These higher oxidation state compounds tend to be unstable in normal conditions. They'll revert to the +3 state if you're not careful. On the other hand, +2 americium compound like americium dichloride can be made by strong reducing agents, but these are also very sensitive and will quickly oxidize back to +3 in air or water. Now, you won't dig up americium in any mine. It's not a natural, abundant element on Earth. In fact, when Earth formed, any original americium that might have been present from supernova debris that created the solar system has long since decayed away. Now, this statement makes the other statement that americium was never present on the Earth wrong. The isotope of americium simply doesn't last for billions of years. For instance, the long-lived isotope Americium-243 has a half-life of about 7,370 years, and Americium-241 has a half-life of 432 years. That's a blink of an eye on geological timescales. So by now, any primordial americium is gone. Scientists have speculated that tiny traces of americium could be generated naturally in uranium deposit, where uranium's radioactive decay and neutron interactions might occasionally produce a couple of americium atoms, but such trace occurrences are extremely small and have not been conclusively observed. Essentially, every appreciable amount of americium in the world has been made by human technology. Now, the primary way that we produce americium is in nuclear reactors. It's a byproduct of nuclear fuel usage. Here's how it works. Reactors usually use uranium-238 and uranium-235 as fuel. When uranium-238 atoms absorb neutrons, which are abundant in reactors, they can transmute into new elements. Uranium-238 absorbs a neutron and becomes uranium-239, which quickly undergoes beta decay, turning a neutron into a proton to become neptunium-239, and then beta decays again into plutonium-239. Plutonium-239 is the well-known fissile material used in bombs and reactors. Now, if plutonium-239 stays in the reactor, it can absorb one or more additional neutrons as well. When plutonium-239 absorbs 2 neutrons, it becomes plutonium-241 through an intermediate plutonium-240 step. Plutonium-241 is unstable with a 14-year half-life, and guess what it decays into? Element 95, americium-241. In other words, over time, plutonium ages into americium. In a nuclear reactor or in spent nuclear fuel, a portion of the plutonium will turn into americium-241. If we leave spent fuel alone for years, the amount of americium grows as plutonium-241 decays. Typically, a ton of spent nuclear fuel, the used fuel rods from a reactor, might contain on the order of 100 grams of americium mixed in with other waste products. Now, nuclear engineers actually consider americium, along with some other isotopes like neptunium and curium, a troublesome, long-lived waste component because its presence complicates disposal. It remains radioactive for a long time. There are ongoing studies about how to deal with this, including potentially burning americium in special reactors or transmuting it into shorter-lived nuclides. But those technologies are still being developed. When needed, we can chemically extract americium from H-plutonium or nuclear waste. For example, in some countries, plutonium separated from old nuclear fuel is allowed to sit and accumulate americium. Then the americium is separated out. Pure americium-241 has actually been available for sale in small quantities since the 1960s. It's quite expensive and difficult to refine, on the order of $1,500 for a gram of americium-241, due to the complex and hazardous process of isolating it. An even heavier isotope like americium-243 costs far more because it's produced in tiny batches. Generally, only specialized nuclear labs handle these processes, and they use multi-stage chemical extraction techniques to isolate americium from a soup of other actinides and fission products in spent fuel. Aside from reactor byproducts, americium can also be deliberately created in particle accelerators or high flux reactors by bombarding plutonium targets. This was how it was first made in 1944. They bombarded plutonium with neutrons and also with alpha particles in a cyclotron. But those methods produce only microscopic amounts. Today, the practical source is still the slow cook method of letting plutonium-241 decay in stored nuclear materials and then harvesting the americium. Now, where can we find americium outside of labs? Well, interestingly, a lot of the americium that exists in the environment today came from the era of the nuclear weapons tests. During the 1950s and 60s, numerous nuclear bombs were detonated in the atmosphere. The plutonium in those bombs produced americium as it aged. Years after those tests, scientists detected americium in the fallout debris. For example, in the Ivy Mike test, the first hydrogen bomb explosion in 1952 created a variety of heavy elements in its fireball. Later analysis of the debris showed significant americium alongside other actinides. The Trinity test site in New Mexico, Los Alamos, the first atomic bomb test in 1945, has a layer of fused sand called trinitite, and we've discussed it in our plutonium episode. And in trinitite samples, decades later, one can find traces of Americium-241 that formed as the plutonium from the bomb decayed. Likewise, places affected by nuclear accidents or incidents can have americium contamination. The Chernobyl disaster in 1986, for instance, released many radioactive elements, including some americium, from the reactor's fuel. Even the crash of a US B-52 bomber carrying hydrogen bombs in Greenland in 1968 spread plutonium, which later yielded americium in the environment. Thankfully, outside these extreme scenarios, the general environment has only minuscule amounts of americium. The average soil might have on the order of 0.01 picocuries per gram from global fallout, a truly tiny radioactivity level. In most places, you would never encounter americium in nature in any meaningful quantity. Now, I could make a joke about the restart of nuclear tests from the United States, but we leave politics out of this video. However, there is one place where you can easily find a pinch of americium: your household smoke detector. If you have a smoke alarm in your house, and you certainly should, there is a high chance it contains Americium-241. In fact, smoke detectors are the reason americium is often called the element in everyone's home. The type of smoke alarm that uses americium is called ionization smoke detector. Inside the detector, there's a tiny capsule of americium dioxide containing roughly 0.3 micrograms of americium-241. This is an incredibly small amount, about 1/3 of a millionth of a gram, but it's enough to do the job. The americium emits a steady stream of alpha particles. These alpha particles ionize the air in a small chamber between two electrodes, meaning they knock electrons off air molecules and create a tiny electric current between the electrodes. Under normal clear air conditions, the current remains constant. However, if smoke enters the detector, the smoke particles absorb the alpha particles or otherwise disrupt the ionization process. This causes the ion current to drop, which the circuitry senses, triggering the alarm. In essence, americium is the active ingredient that makes an ionization smoke detector sensitive to smoke. Why use americium? Well, earlier smoke detectors sometimes used radium-226, another radioactive element, but americium-241 has some advantages. It's a strong source of alpha particles, about 5 times more alpha emission than radium-226, of the same activity, and it emits very little penetration gamma radiation. This makes it efficient at ionizing air without posing a significant external radiation hazard. The alpha particles from the americium source can't even travel more than a few centimeters and are easily stopped by the detector's plastic casing. The gamma rays emitted are minimal, so the radiation dose to people from a mounted smoke detector is essentially negligible. The americium in the detector will very slowly decay over the years. After about 20 years, a few percent of the americium-241 will have transformed into neptunium-237, which is a different radioactive element with a much longer half-life. But even then, the detector still has plenty of americium to function throughout its recommended service life. When smoke alarms are disposed of, the rules vary by region. In many places, you can safely throw them away with the household trash because the americium source is tiny and encased. Some jurisdictions or manufacturers have programs to replace or collect old detectors. It's worth noting, never try to open a smoke detector to get the americium out. The amount is not dangerous when sealed, but you don't want to scatter radioactive material. There's a notorious story of a teenager named David Hahn, sometimes dubbed the radioactive Boy Scout, who in the 1990s collected americium from about 100 smoke detectors trying to build a homemade reactor. He ended up contaminating his surroundings and getting into serious trouble, a testament to why one should not tamper with these devices. So let the americium in your smoke detector quietly do its job and replace the whole unit when it expires. Ionization smoke detectors have saved countless of lives by providing early warning of fires. It's quite poetic that an element discovered in a quest for destruction, nuclear weapons research, is now a guardian in our homes, quietly protecting us. Americium's role here is a prime example of turning swords into plowshares, using nuclear science for beneficial purpose. Or, as others put it, the keys that unlock the gateway of hell also unlock the gateway to heaven. Americium-241's radiation, both alpha particles and the low-energy gamma rays it emits, also find use in industry and research. One common use is as a portable gamma ray source for gauging and analysis. For example, americium sources are used in devices that measure the thickness of materials like glass, paper, or metal sheets. The principle is simple. A gamma beam from americium-241 passes through the material to a detector on the other side. The amount of radiation that gets through indicates how thick or dense the material. Factories use this to perform quality control, for instance, ensuring sheets of glass are the correct uniform thickness. Americium's gamma output is ideal for this purpose because it's basically a single energy around 60 kilo electron volts, which makes measurements easier to interpret. Americium's 241 sources are also used in X-ray fluorescent spectroscopy devices. In these instruments, the gamma or X-rays from americium can excite atoms in a sample to fluorescence, emit secondary X-rays, which helps identify the sample elemental composition. Geologists, archaeologists, and material scientists might use such techniques to analyze the compositions of rocks, artifacts, or metals on site with portable gadgets that have an americium source inside. Another application is in nuclear densometers and moisture gauges. Construction and civil engineering often need to check the density of soil, asphalt, or concrete at building sites. Americium beryllium neutron sources, which we'll describe next, can probe the ground with neutrons and gamma rays to determine moisture content and density without having to take core samples. These devices help ensure roads are properly compacted or that structures have the right concrete density. In an americium beryllium source, often called a MB source, the alpha particles from decaying americium-241 collide with beryllium atoms. Beryllium has a peculiar property when hit by alpha particles. It can undergo a nuclear reaction that spits out neutrons. So an americium beryllium pellet becomes a handy neutron producer. These neutron sources are used in a variety of specialized ways. One prominent use is oil well logging. Companies drilling for oil or gas lower neutron sources in boreholes to map the hydrogen content and thus infer where oil or water may be in rock formations. Neutrons emitted into the surrounding rock can reveal a lot about the rock's composition when detectors pick up the return signals. Americium beryllium neutron sources are also used in science for neutron radiography, imaging objects by their neutron absorption, and in physics experiments where a moderate flux of neutrons is needed. They are favored because they are relatively small and portable compared to a full-scale nuclear reactor or a large particle accelerator neutron source. Americium even played a role in the creation of heavier elements in the periodic table. Scientists use existing heavy elements as targets to create even heavier ones. For example, in 1994, the team of Berkeley took a sample of americium-241 and bombarded it with alpha particles into a cyclotron. This reaction produced element 97, berkelium, for the first time. Similarly, americium-243 has been used as a target to discover elements like nobelium, element 102, by irradiating it with nitrogen ions, and even element 103, lawrencium, via oxygen ions bombardment. In modern times, heavy element research, like attempts to make super heavy elements beyond atomic number 100, sometimes involves starting with americium targets and slamming high energy ions into them. So americium in a way has helped to extend the periodic table by being the seed for new elements. Now, one very exciting potential use of americium is the power source for long-duration space missions. Plutonium-238 has long been used in radioisotope thermoelectric generators, RTGs, to power spacecraft like Voyager probes, Curiosity Mars rover, etc., because plutonium-238 gives off a steady heat that can be turned into electricity. However, plutonium-238 is in short supply and has a half-life of 87 years. Americium-241, with a half-life of 432 years, have been proposed as an alternative for RTGs, especially by the European Space Agency. It produces less heat, around 1/3 of the power of plutonium-238 per gram, but it lasts much longer. In 2019, researchers in the UK demonstrated a small americium power generating, lighting up a light bulb, a proof of concept that americium could be used to generate electricity. An americium-based RTG could potentially power a spacecraft for centuries, enabling missions far into deep space or places where solar power isn't feasible. Imagine probes that could operate for 200, 400 years, sending back data. Americium might make that possible. The downside is that Americium-241 also emits some penetrating radiation, including neutrons, that Plutonium-238 does not, meaning that an RTG would need additional shielding. Nonetheless, the idea of repurposing nuclear waste, extracted americium from spent fuel, into spacecraft batteries is quite appealing, turning a long-lived waste product into a resource for exploration. Beyond RTGs, scientists have brainstormed some wild uses for one particular form of americium, Americium-242. This is an isotope in an excited nuclear state that can release energy extremely rapidly. Americium-242 has an interesting ability to undergo nuclear fission very easily, even as a thin foil, meaning it can potentially produce a huge burst of energy from a small amount of material. Concepts have been proposed where this isotope could fuel a kind of nuclear rocket or high-power nuclear battery. For example, a few kilograms of Americium-242 could in theory yield tens of kilowatts of power continuously for a short duration, on the order of weeks to months. One speculative design imagined a 3.2 kilogram americium nuclear battery producing 140 kilowatts for about 80 days, which is astounding power density. Such a device could propel spacecraft or run high-power systems. The catch? Well, Americium-242 is extremely hard to obtain in quantity. It's produced only in minute amounts during certain nuclear reactions, and isolating it is extremely costly. So for now, these remain theoretical ideas. Perhaps in the future, if technology advances, americium's unusual isotopes might find these futuristic applications. But currently, we're a long way from that. So, is americium the most patriotic element? In name it certainly waves the flag, carrying the very name of America. But, more importantly, americium has served all of humanity in humble but vital ways. It exemplifies how scientific curiosity can find a role that benefits society. The next time you hear a smoke alarm chirp or see the news story about space batteries, you might think of americium, the element with the star-spangled name that went from secret labs to saving lives. Its legacy shows that even elements forged in wartime can become symbols of protection and innovation. Americium's tale is still unfolding as we continue to handle the challenges of nuclear waste or seek power sources for exploring the universe. This element may take on new roles, but one thing is for sure, americium has secured its place in both the periodic table and in our homes, making it an element of both patriotic name and practical fame. Now, we would like to thank the members that support our channel. Thanks for doing that, we really appreciate you. Now, if you think we missed anything, tell us in the comments, and if you want to know more about an element that is created by mankind, watch this video about technetium next.